welcome you to this webinar. And by looking at the names and of the participants, for us here in South Africa, it is good afternoon. For you, might be good morning or even good evening. So, colleagues, welcome by this, and thank you for attending. My name is Roman Lenner. I'm the moderator of this event. I'm also the national chair of the IABSE in South Africa, and we have organized a series of these webinars to promote the knowledge. What we're going to do today, we're going to first listen a little bit about what IABSE is, what is the mission of IABSE. Then we'll play a sponsor video, and then we'll listen to a presentation by our speaker here, which is here on the panel with us, a colleague of mine, Professor Vrablik. Also who's on the panel is our colleagues from Zurich in Switzerland, Brinda Bose and Czech, and we'll be handling this process. Just some admin stuff. Here we have a chat where you guys can talk. We will not attend to the chat, but at the end of this webinar, there's a Q&A button as well. We'll be answering the questions that can be posed in Q&A. So let me first start by introducing IABSE. Let me share my screen. So IABSE is an international organization for bridge and structural engineering. It was established in Zurich in 1929. The mission of IABSE is to exchange knowledge and advance the practice of structural engineering worldwide in the service of the profession and society. The association is about 2,500 people strong, that's spread over 100 countries. There's about 59 national groups. As I said, South Africa is one of the national groups, and I'm the chair of it. We have about 40 to 50 members, and our aim is to share the knowledge that we gain through and disseminate through means of a webinar. IABSE is interested in all aspects of structural engineering, not just the bridge engineering, but all aspects of structural engineering and all types of structures and materials. You can look at the IABSE website for more details. But if we talk about the aspects of structural engineering that we're interested in the association, well, includes the art of science and planning, design, construction, operation, and monitoring of the structures, along with maintenance, rehabilitation, and preservation, which is actually a very, I would say now, modern topic, because we have aging infrastructure, and this is the aspects we are trying to actively look into. But also the demolition and dismantling of structures, while considering the technical, economic, environmental, and aesthetic social aspects. If you look at the IABSE membership, or who are the people that are active or within IABSE, about 50% of our members are in the consulting and design. About a third is in education and research. There are 12% of contractors and some public authorities and owners. The activities, the main activities, the flagship of our activities is the quarterly journal called the Structural Engineering International, where we publish a series of research and technical papers. There's also structural engineering design books, conference proceedings, and guidelines published annually, and there are regular conferences. The next big conference is taking place this year in September in Ghent in Belgium, and some papers have been already accepted for that. What is also specific to IABSE is the different task groups, which are defined by short-term projects, where people get together and either initiate research activity or partake in a research activity. For example, member of TG13, where we look at the partial factors for assessment of existing structures. There are various possibilities of memberships for both individuals and universities, as well as for companies and students. And again, if interested in IABSE, please look at the website. So that is the introduction of IABSE. Now it's my pleasure to introduce the speaker for today, which is Professor Vrablik. He is head of the structural concrete unit at the Czech Technical University in Prague, but he is also structural engineer and technical director at Novak & Partner in Czech Republic. So he has both academic and practical knowledge, and we're very happy to have him here and hear about his expertise in bridge design, long span bridges, pedestrian bridges, but especially the use of the Uhpc. So with that being said, we're gonna now be looking at a video from one of our sponsor, Vrablik EU. So Firat, if you can please play the video.
Vrablik.
So thank you, Vrablik, again for sponsoring. And if you just joined us, you haven't missed the main event yet, which is the presentation by Professor Vrablik. So now I would like to hand it over to him, and let's hear about ultra high performance concrete.
Thank you, Roman, for introducing. I hope everything will run well. I will share my presentation. Please, could you confirm me it is possible to see it? Is it okay?
I see it on my side. Thank you.
Okay, thank you very much. Okay, so nice to be here with you. Let me introduce myself a little bit. As Roman said, my name is Lukas Vrablik. I'm from Czech Technical University in Prague, from Department of Concrete and Masonry Structures. And I also work as a technical director in a Vrablik company. The title of my presentation is the same as the title of the webinar for today. It is the practical use of ultra-high performance concrete, UHPC, as the main material for the superstructures of pedestrian bridges. This is the content of my presentation for today. During the first part, I will speak a little bit about the material properties and about basic information about the UHPC, because it is completely new material. It is a completely new idea about the concrete and new thinking about the concrete. The second part and third part will be about two real structures, two real pedestrian bridges, which we have designed and also which was realized in very close history. And the fourth part will be about the new projects and new projects which we now are designing, and also one project is now under the construction process. Okay, so let me start with first paragraph, first part. What is UHPC? What is the main advantage of the material? UHPC, this short name, it is ultra high performance concrete, or if we add a fiber to concrete, then it is UHPFRC. That means it is the ultra high performance fiber reinforced concrete. It means that to do the basic mass of the concrete, we add the fiber to reinforce the concrete and increase the basic material properties, for example, tensile strength of the concrete. Basic idea or basic characteristic of this material, it is the high strength cement-based composite material, but the advantage is not only high compressive strength. For example, typically we reached 150 megapascal, but also high tensile strength during the bending. It is the more than 20-25 megapascal. Also the high tensile strength during the pure tension, it's approximately 5 or 7 megapascal, but also not mechanical properties and mechanical properties or mechanical behavior of the materials. It is the properties due to the durability, maintenance, and basic behavior of the concrete. You will see that the surface of this material is closed, so it is very important. By this closing of the surface, it is possible to limit the effect, for example, the chemical waters with chemical points from chemical elements, and we could reduce the possible damage of the concrete elements. By the international recommendation, we speak about the UHPC, about materials which compressive strength is more than 110 megapascal. Now it is defined. Typical composition of UHPC is that it is fine-grained aggregate. Usually, maximum diameter of the aggregate is less than 4 millimeters, plus a lot of fillers, chemical fillers. We use optimal granulometry. The reason is to maximize the density of the concrete mass and maximize the density of the concrete volume. Also, we use a high amount of different fillers, especially fly ash, slag, and metakaolin. The reason is increase the characteristic due to the compacting of the concrete and due to the realization, to increase the possibilities of realization of the shapes of different shapes of the concrete elements. Also, we use a high dosage of cement. Approximately, it is 650, maybe more than 650 to 1,000 kilograms per cubic meters. Comparing normal concrete, for normal concrete, we use, for example, 400 kilogram per cubic meters. That means that the dosage of the cement is approximately 2 times higher comparing normal concrete. We use also very low water cement ratio. That means because if we increase the volume of the cement in the concrete mass, we could reduce the water cement ratio. The water cement ratio, typical water cement ratio, is less than 0.25. Comparing to ordinary concrete, again, normal concrete, for example, grade C30, 37, we use a water cement ratio more than 0.4. That means that from the chemical point of view, we don't have enough water to cement hydratation. It is very good because during the time it is possible to obtain something like a self-curing of the concrete. Because if we, for example, some cracks will obtain, we have some cracks in the concrete, and by the cracks it is possible that the water is going through the structure, and then we have we have some amount of the cement which was not used for the hydration. And if we add some water from environment, it is possible again to start with the process of hydration. And we have something like, as I said, self-curing of the concrete and closing of these elements of the cracks. Also, we use, if you want to increase the tensile strength and also to increase produce a better behavior of concrete in the tension, we increase volume, or we add the high volume of fibers. Normally, we use a steel or polymeric microfibers to improve the tensile strength, ductility, brightness, and also the global behavior of the concrete of the UHPC. Very important is also the question of workability. Usually, we use self-compacting, self-leveling concrete. It is something like a honey. You will see a short video of the casting of this concrete, and it is really very close to the honey behavior. It is described by the low water cement ratio and also by the fillers, which increase or which are responsible for this self-leveling behavior of the UHPC. On this slide, you can see typical material properties of UHP FRC. That means ultra high performance fiber reinforced concrete. We have add fibers to the concrete mass. Design compressive strength is more than, as I said, more than 150 megapascal. In this case, we obtain it 180 megapascal. It is important to say that the strength level is affected by the type of the elements on which you produce the tests. If you decrease the dimensions and decrease the volume of the UHPC, which is used for the testing, the strength will increase. So it is something like the effect of the, it is something like the size effect. And it is important when you define the grade which you need for your design, for your project, you have not only define the appropriate value of the strength, but also the way how to test it, and also the type of the elements on which you will produce the tests. As I said, very important is a question about the tensile strength, especially flexure tensile strength. Comparing normal concrete, we have something like 10 times higher, because normally we obtain the value approximately 20 megapascal. Design tensile strength is pure tension is less than 10 megapascal. It's approximately 10 megapascal. It is the maximum. Also, the value of elastic modulus is a little bit higher comparing to normal concrete. Pylon ratio is the same. Also, the linear expansion coefficient due to the temperature loading. Important is question about the creep and about the shrinkage. About the creep, we have a very small coefficient of the creep. That means it is possible to say that the creep could be neglected in some special arrangement and special type of the analysis. So the creep is very low, again, comparing normal concrete. Normally, in the question of the shrinkage, we have only drying shrinkage. So we have only shrinkage in the initial stage of the behavior of the concrete. So it is important, for example, during the casting of the element. But after casting, after a few days, it is possible to see that no shrinkage will appear on the structures. Again, it is very important for the designing, because you have to think only think about the shrinkage during the casting, during the prepare of the casting of the element. But if you put the element, precast element, to the final statical scheme, to the final statical structures, you could neglect the effect of the shrinkage. So again, very important and very interesting comparing to the normal concrete. And normal concrete, could be a problem, the question of the shrinkage and creep. With UHPC, we don't have a problem with these two biological phenomena of the behavior of the concrete. What is the main difference between the normal concrete and between the UHPC? It is possible here. It is possible to see on this picture. It is the typical diagram in horizontal axis. It is the thickness of the cracks, and on the vertical axis, it is the tensile stress in the concrete. It is the tensile stress during the flexure, during the bending. The maximum value is approximately 20 megapascal, as I said during my last slides. And also, we could see there is 3 phases of the behavior. The first one, it is the elastic behavior. That means that if you increase the strain, you will increase also by the same level, by the same multiplication, you will obtain the same stresses. In this area, it is the hardening. It is very close to the behavior of the steel. After hardening part, you will reach the maximum value of the bending tensile stress. It is the bending tensile strength of the concrete. And then it is the effect of the softening. But the damage of the concrete, it is not a damage in the point, but you can see that the material has a great ductility. If you, for example, compare it, the area under the blue line, it is something like the energy from the mathematical and physical point of view. And if you compare the energy, which is important if you want to damage, if you want to destroy this element in the tangent by the flexure tests. And if you compare this area, this energy with normal concrete, it is, for example, 10 times, 15 times higher comparing the normal concrete. This is a great advantage of the UHPC. And if we take into account this behavior, it is possible to design very thick element. We could increase the slenderness of the element, and also we could reduce the dimensions of the members. So it is very good for the designing. And also if we take into account the effect of the increasing compressive strength and also the effect of the flexure tensile strength, we could really produce designing of the cross sections. If we compare it, for example, with the steel, it is very similar, also the dimensions and also the shapes of these members. Again, it is also something like a conclusion about the material behavior. On previous slide, you saw the normal real tests, and this is the theory. The first stage, again, as I said, elastic behavior. This is the hardening between the end of the elastic behavior and between the reaching the top of the material. It is the tensile strength during the bending, and then it is the softening. And again, the gray area, it is the energy. So the energy is very high comparing normal concrete. And again, it produces great advantages for the designing. Normally, again, this value is approximately more than 20 megapascal. This is only in this occasion, only small number of small volume of fibers were used. So you could see that the value of the tensile strength during the bending, then it is limited. So it is possible to say that the conclusion that the value of the tensile strength of UHPC is affected by the volume of the fibers. If you increase the volume of the fibers, you will also increase the value of the tensile strength concrete during the bending. Very important, the effect of the shrinkage and creep, very low, so could be neglected. Only during the casting, you have to take into account the effect of the drying shrinkage, for example, due to the shortening of the element, and for example, to produce special elements or if you produce precast elements, you have to take into account this phenomenon, for example, to increase a little bit the length of the elements because of due to the shrinkage. I think very nice comparison is these three pictures, three grades of the concrete, normal concrete 330-37, then high straight concrete C80-95 and UHPC. If you compare the density, or if you compare the volume of the concrete, you can see the aggregate. Also, you can see the volume of the cement between the aggregate. UHPC, the volume is completely closed. There is no hollows, no bubbles, completely closed materials. And this is very important for the long-term behavior, not long-term behavior due to the creep, due to the shrinkage, but it is long-term behavior due to the durability, especially the effect of the chemical attacks from the environment. UHPC is closed, so for example, it is not necessary to produce the waterproofing surface on these elements. Also, for example, you could reduce the distance between the bars and between the sides of the concrete. And also, again, you could reduce the dimensions, because also very often the dimensions of the concrete elements are affected by this area of the cover, by this dimension of the cover of the reinforced concrete. So if you could reduce the size of the cover, you could reduce the dimension of the concrete, concrete element. Short comparison between basic materials, UHPC, steel, and normal concrete. UHPC, as I said, density of the material, or how much material you will spend for 1 meter of the element, is very close from UHPC to the steel. It is 140 kilograms per meter, comparing 110 kilograms per meter for the steel. If we go to the prestressed concrete area, prestressed concrete range, we will obtain elements which we have to increase the height of the elements due to the increasing of the stiffness, of course, and also increasing or decreasing the tensile strength, tensile stress in the concrete. Then we obtain something like more than 450 kilograms per meter. And if we don't want to use a prestressing, only for the reinforced concrete, we obtain more than 500 kilograms per meter. So if we compare reinforced concrete with UHPC, it is approximately 3 times, something like 3 times higher. Is reinforced concrete comparing to UHPC. So if you compare the volume of the concrete aggregate, which is necessary for UHPC element, comparing to the normal reinforced concrete, for example, we will have a single span bridge. And also because we have to take into account the effect that in normal concrete is the volume or water cement ratio, or the volume of the cement is 2 times lower comparing to UHPC. So normally we obtain that the UHPC, the benefit of using UHPC is approximately 1.5 to 2 times better solution compared to normal reinforced concrete. As I said, the great advantage of the UHPC is not only mechanical point of view, it is also the effect of the closing of the matrix, closing of the volume of the concrete. Again, comparing between UHPC on the left side and normal concrete. This is the aggregate, this is the cement between the aggregate. In UHPC, the volume, the matrix is completely closed. On the concrete, there are some hollows, there are some spaces, and by these hollows, by these spaces, it is possible that the aggressive water from the environment, it is possible that it goes through the structures and it could attack, for example, the reinforcement. Again, it is the question of the surface. UHPC compared to normal concrete, surface of UHPC completely closed. Normal concrete, hollows, small, very small cracks. And by these hollows and by these cracks, again, aggressive water could go through the concrete and attack the reinforcement, and some corrosion could appear. About the water content, as I said, the water content is very small in UHPC. We use normally approximately 5%, comparing 20% for the normal concrete. Again, it is the question, as I said, the question of the self-curing of the UHPC, because we have lots of cement, and this cement is not used for the hydration during the initial stage of the behavior of the concrete and the initial stage of behavior of the material. So we have, it is possible then to use this not used concrete for the curing. As I said, for example, during some cracks will appear by the water, connection between the water from the environment and this free cement, these cracks will be closed. Also, what is very important from the aesthetic point of view and from the architecture point of view is a color integrity of the concrete. If we compare UHPC again with concrete, with normal concrete, it is not a problem to add a special colors elements to the concrete mass, and you could obtain, for example, black concrete pedestrian bridge or red, it depends on you, and the color is constantly distributed through the whole volume of the concrete, not only, for example, surface as for the normal concrete. What is important to say as this something like a disadvantage of the UHPC nowadays, the best solution for use UHPC is using for the precast elements. That means that the UHPC elements are produced in special fabrics, in special precasting buildings, and then we use these elements for this final statical solution, final statical scheme, final structures. So we have to produce, we have to think about the possible how to connect these members together, how to solve the joints between the members. Maybe sometimes in the future, we could think also about the casting in situ of the UHPC, but still it is the question of the drying shrinkage, as I spoke about it. And still it is the question about the producing of UHPC, because if you want to produce UHPC, it is a very difficult and very important chemical process. We have to produce the mix very good. We have add lots of additives, and the ratios are strictly described. So we couldn't produce a mistake in the phase of the producing of the concrete mix. So maybe in the future we could change it, maybe in some years. But now the best solution for use UHPC, it is used for the precast elements. Okay, now we will speak about two real bridges in Czech Republic. The first one, it is the pedestrian bridge in Přibor. Přibor, it is a very small city in the east part of Bohemia. As you can see, we have designed it and then produced the single span pedestrian bridge. On the right side, you can see the visualization. It was the first idea about the bridge. The idea was to produce only straight line without any additional geometric parameters, only the straight line. And also the idea was to limit the thickness of the element. So we have decided to use a UHPC as a main material. As you can see on this information, the total length of the single span structure, or the length of the span, is 35 meters. The height of the cross section is only 0.8 meter. If we want to produce something like a height to span ratio, it is 1:44. It is completely out of normal idea about this type of the structures, because normally we use this ratio approximately 1:20. As I said about the disadvantage of the UHPC, it is necessary to produce the precast elements. So in this case, the superstructure was divided to the 5 separate precast elements, 3 normal elements, which were situated in the middle part of the structures, and 2 elements, side elements. The geometry of the elements was the same, only in the side elements which are situated above the abutments. There were some changes of the thickness in the thickness of the walls, outer walls. The reason was that we have to produce the anchorage of the prestressing tendons. Because of this structure is made by the UHPC elements, precast elements, it was necessary to satisfy the condition of stresses in the joints. So normal stresses in the joints should satisfy the condition that for each possible loading combination, we have minimum 1 megapascal in compression in this joint. So that's why we produce the prestressing by 3 tendons. The tendons are realized by 17 monostrands cables. They are going through the walls, as you can see in these pictures. And the geometry of the tendons was described by the basic statical behavior. As I said, it is the single span structures. That means the main loading is done by the dead load, by the self-weight of the structures. So the shape of the prestressing table was described by the second order parabola. And this second order parabola produce uniformly distributed loading, equivalent loading. And this loading was the same as the loading due to the self-weight with opposite direction. This is definition, as I said, definition of the segments situated above the abutments. What was interesting, because we want to reduce the volume of the concrete. There are big hollows in the superstructures, in the segments. On one side, we want to reduce the volume of the concrete. On the other side, it is impossible to have a hollow or have this hollow in the structures, and it is impossible to make an inspection of this hollow. So we have decided to use a polystyrene, that these hollows were filled by the polystyrene members. It was a big challenge, because during the casting, it was necessary to fix the position of these polystyrene members. You will see it on next slides from the casting of the elements. This is the shape of the typical segment. It is something like a box with hollows, with one intermediate cross beams, and also the same cross beams were used in the outer area of the element. In the joints, it was important to reduce the cross-section area, because, as I said, we have to satisfy the condition for the stress in this joint during the service life of the structures. So if you reduce the cross-section area, you reduce the number by which you divide the stress, especially the normal, the effect of the axial force of the prestressing. So then you obtain a little bit more benefit of the prestressing in this area, and it was important. Some pictures from the casting and from produce of the elements. We use a contact way how to produce of the elements. That means on one side, the previous segments make a formwork, define the shape of the sides for next segment. You can see reinforcement and also the blue polystyrene members. As I said, it was a big challenge because during the casting, naturally the polystyrene elements want to go up. So it was necessary to fix them to the right position. We used a big concrete block, which was situated above the elements. And by these steel ties, steel members, the position of the polystyrene blocks were fixed. Position was fixed. Some details, very important due to the durability of the structures, is the detail of the prestressing or the curing of prestressing going through the joint. We used a special Lia seal couplers from the company Freyssinet. It is a special plastic couplers. You can see these blue elements. And by these couplers, it is possible to satisfy the conditions that it is completely waterproofing of prestressing, waterproof solution for the prestressing, which is going through the joints. Because if normally it is very dangerous, this joint is not so good detail for the global behavior, because in this joint it's possible that some water goes through the joint between the segments, and then the water, if you don't have a good or appropriate solution for this tendons tube, then the waters could attack the prestressing steel, and also some corrosion could reappear, and corrosion could reduce the area of the prestressing steel, and you will reduce the volume of the prestressing, or you will reduce the prestressing level of the structure. What is very nice, it is the detail of the surface during the casting. You could see the lots of bubbles on the surface. Now I will try to show you a video. I hope it will operate. And another video. It is the testing. I think you could see the honey consistency of the concrete, especially on the first video. If you compare it with normal concrete, it is completely different. It is a self-compacting effect, but also not typical self-compacting concrete. It is, again, as I said, very close to the honey behavior. Okay, short information about the computational analysis of the bridge. As I said, it is the segmental bridge with 5 separate precast elements. Very important is to satisfy the conditions of the stresses, especially in the joints. So you have to satisfy that for all possible loading combinations, you have a still compression in the joints. You can see the results from the analysis. We use a combination of very simple beam model. This model was used for the time-dependent analysis because we want to study also the prestressing losses and the effect of the prestressing losses for the global behavior of the structures. And also we use a special three-dimensional model, three-dimensional slab model, especially for the dynamic analysis of the structures due to acceleration and to satisfy the conditions for the acceleration of the pedestrian bridge. But on this picture below, I'm sorry. On this picture below, this is the analysis of the stresses. Especially this one was important because it is the analysis of the stresses, normal stresses especially in the joint area. at the end of the service life. That means after 100 years after casting. And you can see that we have still compression in the joint area. The compression was approximately 1.5 megapascal, so it's enough because the condition is minimum 1 megapascal in compression in this area. Also very important is the question of the dynamic behavior of this bridge, of these structures, because again, it is the simply supported beam. The length of the span is 35.5 meters, and the depth of the cross section is only 0.8. So it could be described that the stiffness of the bridge structure is very low. But what is benefit? It is the effect of the concrete for the dynamic behavior. You can see the 5 first natural frequencies of the structures. So for us was a little bit dangerous, the first one, because it is the bending shape of the superstructures. But if we produce a global analysis of the dynamic behavior or the analysis of the structures, which is so affected by the harmonic loading, we have some limits for the maximum acceleration. As you can see from the computation, we obtain 0.1. It is the maximum acceleration for this harmonic loading, which is realized by the people going through the bridge. And the limits, which is affected by the first natural frequency, is 0.58. So the behavior of the bridge is completely okay. If you go through the bridge, you could feel the movement of the bridge, but for your safety and for your good for the behavior, it is not a problem, because the value because the value of the acceleration is very low comparing the limits, which is done by the standards for the pedestrian bridges. Some pictures from the not only from the casting but also from the construction process. On the left side, you can see the final view of the first segment. On the right side, it is the casting of the segments in during the casting of another one. This is the casting. This is the construction sequences of the segments on the rear position of the structures. In this picture, you could see that we use the temporary scaffolding, temporary steel structures. So we have a very good conditions to produce the construction of the segments. The connections between the segments, or the joint between the segments, are filled were filled by special glue. It is a special polymer glue. You can see here it is the preparation for the connection. What is important that for the initiation process of the glue, if you want to produce some strength of the glue, you have to produce the compression. But as I said, we produce the compression for the whole structure by the prestressing tendons, with second order parabola shape. So during the construction sequences, we have to use temporary prestressing by the joint. It was done by special, you can see here the member, it was a special steel element. Every segment on the upper part and also on the bottom part has a special steel element. And these steel elements were connected by the bars during the construction process, by the prestressing bars. And by the prestressing of these bars, we could produce the compression in the joints for the glue, or for the initiation process of the increasing of the strength of the glue. So it was the interesting but very important to produce the closing of the joint, and also for the satisfy the conditions for the glue. And also it is important to satisfy the condition for the closing of the couplers, liaisal couplers, because it is important to put them together. It is not only the connection is done only not by the surface are close together. You have to move with some elements to the through the another one. So this effect with the bars was very good also for this way of the construction of the prestressing. Some information about the tests of these elements, about the strength, and also about the compression strength, and also about the modulus of elasticity, and also about the flexure strength on the beam. About the modulus of elasticity, normally average value was approximately 48 gigapascal. Again, comparing normal concrete, it is a little bit higher. If we study compressive strength, it depends on the shape of the element, and also it depends on the dimensions of the elements. For the cylinder, we obtain a compressive strength approximately 140 megapascal. For the cube, for example, a cube with the dimensions of sides 100 millimeters, the average value of the compressive strength is 148 megapascal. But for the beam, very small beam, we use this small beam 40 with the cross-section side dimension 40 millimeters and the length 160 millimeters. We use it to test the flexure energy. It is the testing of the flexure strength of the concrete. And for this element, we obtain it the value of the compressive strength approximately 175 megapascal. Again, as I said, the value of the strength is affected by the dimensions and is affected by the shape of the element which is used for the testing. Very interesting is question about the flexure strength, because for the normal beam, that means beam with the cross-section area, or with the cross-section by the or the dimension of the cross-section 100 millimeters, and the length of the beam is 400 millimeters. We obtain 50 megapascal. But for the smaller beam, again, it is the same 40 millimeters for the cross-section and 160 millimeters length of the beam. We obtain 33 megapascal. Again, comparing normal concrete, completely new material, completely new idea. You can see the final view of the bridge. Again, for this bridge was not used any waterproofing, any special arrangement of the upper surface. The surface which you can see on the picture is a direct surface of the precast elements. So if you go through the bridge, you are going through over the upper part of the elements without any additional members, additional layers. This is the night view of the bridge. I think again, it is very close to the idea about the steel bridge, not about the concrete bridge, because the ratio between the depth of the cross-section and the length of the bridge is 1:44, and again, completely different about the thinking about normal concrete and normal solution for the normal concrete structures. Okay, the next one, it is the pedestrian bridge in Lužec. This pedestrian bridge is situated very close to Prague, the capital of the Czech Republic. It is situated, or it goes over the river Vltava, which is going also from Prague. As you can see, the main statical scheme of the bridge is the, as I said, cable stayed bridge. The length of the main span is 99 meters, and the length of the side span is approximately 32 meters. About the basic idea of the superstructures, the superstructure is realized by 31 typical segments. The length of the typical segment is 4 meters. On the side, there were used a typical segment with length 2 meters, and also special part you can see here, and in this area, it was the part of superstructures realized by casting in situ. On one side, on this left side, on this abutment 01, the connections between the abutment and between the superstructures was done by this casting in situ element and by two bearings. On this area, on the right side, there is a rigid connection between the superstructures and between the abutment, again realized by casting in situ element. Because it is a cable-stay bridge, it was necessary to use a pylon. The pylon is done by steel. It is the box cross section, two box cross section. You will see a typical scheme of the bridge on the next slides. On the bottom area, the box of the steel is filled by the concrete. It is a very good solution if you want to increase the stiffness of the element, and also if you want, for example, produce something like a protection of the steel. For example, during the flood, it is possible some attack by the elements, which is by flood going on the river. And by this filling of the steel by the concrete, I think it could help you to increase the stiffness and also increase the safety of the structure. About the construction process, this area, this gray area, and also this one area, it was erected on the temporary supports, on the temporary scaffolding, and this main part was erected by the balance cantilevers. You will see it again on the next slides. Very important is also to define the stability, or to satisfy the conditions of the stability of the structures, because if you compare the length of the span, the main span, it is approximately 100 meters, comparing to the side span, it is possible to see that if I put a loading here, the structures want to go from this point, the bending of the pylons will appear, and also structures want to fall down in this direction. So it is necessary, it will be possible, for example, increase the dead load in this area, but in this case it was impossible because we want to use the same structure solution, the straight, very slim element through the whole length of the bridge. So again, we have decided to produce the rigid connections between the superstructures and the abutment, and also the last pair of the hangers are directly connected to the abutment, and by the ground anchor it is connected to the or founded to the ground. So by this tension, for example, again, if I put a loading, I will produce bending of the pylons, but the bending of the pylon is limited by these hangers, and the tension from these hangers is going directly by the volume of the abutment to this ground anchors. So by this solution, the conditions for the stability of the structure is described and is satisfied. Typical cross-section and typical or the shape of the pylon. The typical cross-section is described by the geometry of the Uhpc element, precast element. Very typical, or it is a typical solution that on site we have something like a longitudinal beam, then the slab between the two beams. The thickness of the slab is very low, it is only 60 millimeters, and the width of the beam is 400 millimeters. Total depth of the cross section is 500 millimeters. We have also something like a cross beams on the Uhpc elements. By these cross beams, we increase the stiffness of the element, but we use them also as a support for the longitudinal prestressing, which are going through these hollows, through all the length of the bridge. This is the view of the pylon. The pylon, as I said, is completely realized by the steel as a main material. Only this bottom area, the steel box, is filled by the concrete. What is interesting, that there is no connection between the superstructures and between the pylon. So that means, if we go back to this slide, that from this point till this point, it is a one structure, one beam, without any supports. Of course, the vertical part of forces from the hangers produce something like a support for the superstructures, but due to the but for the normal point of view, there is no support, only in this area, in this abutment, and also this rigid by the bearings, and in this area by the rigid connection between the bearing, between the superstructure and between the abutment. Typical shape of the beam of the UHPC element. Again, this is the basic geometry. Interesting is the connection between the hangers and between the UHPC element. Again, maybe I'm sorry, back to the longitudinal section. The distance between the hangers connections and between the connections between hangers and between the superstructure is 8 meters, and the length of the segment is only 4 meters. That means that only every second element is joined with hangers or supported by the hangers. So it was a big challenge to define the right conditions, how to satisfy again the conditions of the stresses, because normally each segment has its own hanger. In this occasion, it was not used this solution because we want to reduce the length of the UHPC element for producing, for the casting. So this joint is without, or this element is without any connection with hangers. And then it was necessary if we want to satisfy the conditions, we have to produce some temporary prestressing. I will show you on next slide. So back to the solution about the connection between the hangers and between the UHPC element. Special steel element was used. This special steel element was put to the formwork during the casting of the element. This is the solution of the steel element in the cross section and the longitudinal section. It is the typical solution also with the connection between the steel element and between the hangers. We use a special small hollows for the reinforcement which is going through this steel element. This is the reinforcement bars, and also another hollows for the concrete. So during the casting, the concrete is going through the hollows, so the element is completely filled or completely integrated to the concrete volume of the UHPC element. Also interesting and very important is a solution of the joint. You can see here on this picture. On the joint, this is the end of the segment, and because of the shape of the geometry of the segment in the joint area, again the idea was to reduce, and it is still the same, reduce the cross-section area in the joint. So this small cantilever, as you can see here, it was produced to make a connection between two elements together. So by this cantilevers, the connections is defined. In this part, special seal was realized, and the space or the volume between two segments was filled by a special material. It was the material which is material done by or realized by the Sika group. It is a special polymeric material with very good mechanical properties, and also very good properties due to the durability of the structures. And also it is the high strength material. Approximately the compressive strength of this material is more than 120 megapascal. So now you can see the picture of the one element. It is the element with future connections with the hangers, and this is the detail of the hanger connection to the element. Here you can see the hollow. This hollow were used for the prestressing bars it was the temporary prestressing bars which were used during the construction process, because the same problem comparing to the previous bridge. Again, we have to produce the compression between two elements during the construction process. So for this solution, to satisfy this condition, we use the prestressing bars, which are situated directly in this hollow and going through the UHPC element. About the hangers, it is very important, because the hangers are the main elements to satisfy the conditions of the stability, and also if you want to produce this type of the bridge, it is necessary to have hangers. For the structures, we use the hangers from Radiali company. It is the Italian company. The type of the hangers is called FLC. That means it is the full locked core strengths. You can see basic idea about the strengths, about the hanger solutions. So the surface and also the volume of the steel hangers again is completely closed. Very important is also the distribution of the diameters of the hangers, because the distribution of the diameters produce distribution of the stiffness of the hangers, or is described by the basic or the elementary behavior of the structure. So for this hangers, we used one pair of hangers FLC diameter 35 millimeters. And for this reverse hangers, we use 36, 60, and 64. Especially these hangers are very important, because by these hangers, the stability is described of the structures. The pylon is fixed by these hangers in the position, and these hangers produce straight connection between the pylons, between the head of the pylon and between the abutment, as you can see here, and of course between the ground anchor for the foundations. Some basic view about the hangers and about the connections between the hangers and superstructure. This is a typical view of the hangers. This is the solution of connection between the reverse hanger. It is the diameter 64 millimeters, and the connection between this hanger and between the abutment, and by the abutment with the ground. Solution, when we finished the bridge. You can see here, this is the detail of the connection of the, connection of the hanger and between the element. Of course, it was necessary to produce the prestressing of the hangers, because the self-weight of the superstructure is very low comparing to the, if you want to satisfy the condition of the stability, we have to produce a little bit higher tension in the hangers, especially for these hangers, because the angle between the superstructure and between the hanger is small. So it was necessary to produce the prestressing. The prestressing was done by hydraulic jack and by special arrangement of steel elements. It is the typical solution, and typical solution described by company VSL, which was responsible for the process of prestressing, installation and prestressing of the tendons. So the tendons are, the contractor of the tendons again was a company Radiali, and VSL was responsible for the installation and for the prestressing or activation of the tendons. Maybe I forgot that the general contractor was a group Hochtief, which was responsible for the construction process of the bridge. Interesting was also the construction process, because, as I said in the beginning, it was a combination of casting of some part of the superstructures, Then we use special temporary supports for some number of segments, and the rest of the structures was realized by the balance cantilever. So this is the first stage. You can see the temporary scaffolding, and some UHPC elements were placed in this area to the right position, and also the connection between the UHPC element and this casting in situ element, which is directly connected to the abutment, was realized in this phase. After finishing, we put there the first group of the hangers, and we begin with the balance cantilever method. For these stages, we use a special moving formwork. This special moving formwork, it was a steel structures. You will see it on the next slides. And also for this moving formwork, we use a temporary hanger, which were connected between this steel element and between the head of the pylon. So this is the stages of the some stages of the balance cantilever method. This is the final stage of the balance cantilever. It was really very interesting. You will see it on the photo, because in this stage, no temporary scaffolding, no temporary supports were here. It was our idea as a designer, but it was not necessary, because if you put a loading here, you will obtain reducing of the reaction, reducing of the forces. So after probably 3 or 4 cycles of the balance cantilever methods, it was not necessary to have supports here. So in this stage, the length of the cantilevers from this point to this point was 72 meters approximately, and this is 38. So we have something like a cantilever, again without any connection between the superstructure and between the pylon, only connected by the hangers with the pylon, and by this structure element casting in situ between the abutment and between the superstructure, but it was enough. So it was a very interesting part of the previous year. During the construction process was realized. It was approximately in this time. For me, it was really very interesting part of my professional life, because every 2 days I have to define the geometry. I have to define the prestressing of the hangers and prestressing of the temporary bars. The speed of the construction process was very high. As I said, probably every 2 or 3 days, next 2 elements were added to the previous part. So I spent lots of nights for the calculations to define the geometry and define the right conditions. So back to the description of the construction process. When we reached the left side bank, it was possible to produce also this temporary support for the rest of the superstructure. Again, some precast elements were put there to the right position, and the closing element above abutment was realized. When we finished with the realization of the construction of the superstructures, it was possible to produce the longitudinal prestressing. By the longitudinal prestressing, which is situated under the UHPC elements in the hollows going through the cross beams of the UHPC element, we produce the complete compression between the segments, between the precast elements, and then we produce the rest of the bridge, some arrangement of the surface under the bridge, and also the final arrangement of the bridge, final arrangement of the superstructure. About the statical and computational analysis, we used lots of computational model. It was necessary to take into account nonlinear effect, especially nonlinear effect of hangers and nonlinear effect of the superstructures, because there is no flexure stiffness of the element. So it was necessary to take it into account, and all calculation were nonlinear and based on the nonlinear theory. Very important was a checking of the stresses and checking of the geometry. On this picture, it is the checking of the geometry or the development of the geometry of the superstructure during the construction stages. You can see that through the construction stages, the superstructure, because you increase the length of the cantilevers, will go down, and we have to produce the precambering. The precambering was realized by the prestressing, by the prestressing of temporary hangers, which connected the steel support elements to the pylon. And also it was important to satisfy the condition of stresses. This is the final stress distribution. Especially important is this red dots, because it is the distribution of normal stresses in the bottom area of the cross sections. It is the end of the service life without take into account the effect of the construction stages. That means that there is no effect of the horizontal forces from the hangers. It is only the effect of the longitudinal prestressing, the rest of the dead load, the effect of temperature, the effect of the creep, very small due to the behavior of the UHPC, and the effect of the life load. As you can see, in this occasion, in this situation, we still satisfy the conditions that we don't have a tension in the joints area between the segments, between the UHPC elements. But if we take into account also the effect of the compression of the construction process, we obtain more than 5 megapascal in compression in each part of the superstructure. So let me introduce some pictures during the construction process. This is the beginning.
Lukas, if I just may, if we can start slowly wrapping up, because we have some questions and we still need to answer the questions, but we want you to finish, but just keep time in mind. Thank you.
Okay, I will finish it. Okay, I will go through the construction process I will increase the speed. This is interesting. It is the balanced cantilever construction process. Special steel member used for the casting of the UHPC element. You can see special support. By this support, it was possible to define the right position and the right geometry. And again, the temporary hangers, which was used to connect this steel element to the pylon. Very nice motion pictures of movement of segments from this position to the final position on the structure. For this movement, a big crane was used, as you can see. This is the final stage of the balanced cantilever stages, or final stage of this way of the construction. I think very nice picture without any supports, more than 110 meters of the free structure above the river. And this is final view of the bridge. It is very close after finishing of the works. Detailed view of the surface. Again, the surface is closed. You can see very small hollows. It is done by the bubbles, but the surface is closed. Very nice, and also the geometry is very good. And again, some pictures of the bridge. Again, some detail of the surface. Only some hollows of the bubbles. So it is done by the bubbles during the casting. Nice view if you are under the bridge, and you will see the prestressing tendons going through the precast elements, and in this joint area it produces the compression, which is important for us. Night view of the bridge, and night detail of the surface with the light, and general view of the bridge during the night. Now I will switch on time-lapse video. It will be very quick, I hope. You will see all the construction process. I think it will be only 1 minute. maybe I will switch off this and I will go to the next slide. Then I have only 4 slides about the new projects. Now we work on design of the new pedestrian bridge here in Prague. It will be also done by the UHPC element. You can see the basic view, and this is some visualization. Again, it will be UHPC precast elements, which were connected by the tendon. The position of it is possible to see the position of the tendon. It will be also possible to see it during the all service life. So it is something like also for the common people to say what is very important part of the bridge. So we want to make some special arrangement to see this prestressing. It is not a question only about the statical, but also a statical point of view. And the next one, which is now under the construction, it is the bridge over River Labe in Hradec Králové. Hradec Králové is a city in the east part of the Bohemia. We will produce this type of the structures, and for the superstructure, again, we will use this type of precast UHPC element. Again, the shape geometry is very similar to the bridge in Lužec. This bridge is now under construction. We have begun with the preparation of the formwork for the casting of the elements, and I think that next year, till the summer of the next year, the superstructure or the structure will be open. So thank you very much for your kind attention, and I'm sorry for 22 minutes more for my presentation.
That's not a problem at all. We're very thankful for your presentation. Thank you very much. There's some questions already posted there, so if guys are still interested in posting a question, please use the Q&A. And meanwhile, we'll try to go through them. So the first question is, in Dubai, there is a restriction on the allowable strength larger than 85 megapascals. So what do you think about that? Should there be a restriction?
85 megapascal?
Yes.
I don't know the reason why to use this restriction.
Okay. Yeah. Perhaps, yeah, authorities have some sort of a reason. So we're not quite sure.
From the mechanical point of view, it is not necessary to make a restriction for the strength.
Yeah. Then there's a question about the residual strength after propagation, the diagram that was shown initially when you were plotting the crack mouth opening. Was it for UHPC or was it UHPFRC? Was it with fibers or without?
UHPFRC. Normally, we don't use pure UHPC because it is not so good to use only UHPC. Normally, we use a UHPFRC, and then the stiffening and also this typical behavior is done by the fibers which are connected to the volume of the concrete.
Okay, interesting. Thank you. Another question is there, how can you achieve such a low shrinkage and creep values for UHPC? There was also a slide shown with some values, and the question is, why are they so low?
It is done by the basic chemical behavior of the concrete, because you increase the volume of the cement in the concrete mass, and also by the additives which are added to the mix. So by this definition of the mixture, it is possible to decrease by this the shrinkage to the volume, as I said.
Okay, thank you.
It is not a question it is a question for my colleague, because it is a chemical point of view and material point of view, but I only have these results, and the results are very good for us as a designers.
That's for the specialist that does the mix design.
And very often it is impossible to obtain the definition of the mix from the producers, because it is the know-how how to produce the UHPC. For example, 10 years ago, it was possible to buy a ductile. It was the first using of the UHPC. It was a special mix. You obtained a special, for example, 1 kilo or 10 kilo of the ductile. You add only water, and it was finished. Now, if you want to produce UHPC, you will define your properties, mechanical properties, and you will obtain the members. But you don't. It is impossible to obtain right mixture and right, for example, volume of aggregate, volume of cement, volume of water. It is impossible. It is a know-how of the contractor.
So they keep it secret and they just deliver the product.
It's completely secret. But
Okay,
it works. It works.
There was a question about the segmental bridge when the segments were connected together. What were the construction tolerances?
It is approximately 5 millimeters plus minus 5 millimeters.
Okay. So
we are going to the steel area not only with mechanical behavior but also with the construction process. So the dimensions are described by the millimeters, and also this construction process is described and satisfied by the millimeters.
So not like reinforced concrete when here and there 10 millimeters doesn't matter.
No. In this area it is impossible.
Okay. Is there any study about the use of UHPC in a hot weather environment? I think it's from our colleagues from Middle East, perhaps.
I don't know directly, but I think if you use precast elements, it is not a problem to use it. What is a problem? It is the casting. It is the casting of the element. But as I said, now the UHPC is impossible to use for the elements casting in situ. So if you produce the cast as a precast elements, there is no problem to reduce the temperature during the casting, for example, in special building. But if you finished with the casting, finished with the producing of the element, you can use it anywhere. It is not a problem.
So that's it's not very sensitive to hot environment. And once
very
finished,
often, maybe what is special, very often we could use a fiber reinforced UHPC as a protection for the fire. So if you protect, for example, steel member for the fire, it is possible to use a UHPC element. So we will use something like a UHPC shell over the steel element or over the normal concrete element, and the protection is very good.
So it's actually better than...
Yeah, it is better. It is better.
Okay. Another question here is, can we cast UHPC on curved surfaces or formworks? And I think achieve...
Yeah, it depends. Normally, the maximum longitudinal or the surface could be, it is straight without any curvature. But sometimes it is possible, for example, that the 0.5% is possible, but no more.
Okay, so rather straight, keep it straight.
Yeah.
There's a question about the resistance factors, the safety of the UHPC, and there's also another question I read about the design norm. Is there such a thing, and how do we quantify the resistance? Would it be the same as for normal concrete, or
it is still the same? It is still the same, but what is important that we don't have a now standard recommendation for UHPC. So we are out of the limits of the Eurocodes and also from the model code, because Eurocode and model code is described for the concrete. I think it is the grade C90 or 105. I think it is the maximum grade of the concrete. If you increase the grade, if you increase the strength, we don't have a special recommendations. Normally, we have something, not a standard rules, but we have a recommendations, for example, which is described by the results from the research. So we could have something like the supports for the designers. But for the question of resistance and ultimate limit state, it is still same the question as for the normal concrete. But what is possible that we could say that the concrete is possible to take into account in the tangent area. It is a very big difference comparing normal concrete.
So there's no code, and we still treat it as normal concrete, even though we know it's not.
Very often, for example, for ultimate limit state or for the resistance, it's necessary to use a nonlinear modeling. For example, we use a program Athena. To the program Athena, we define the real material behavior, which is described by the results of the experiment, especially the behavior in the tangent. And by this definition, it is possible to produce this type of analysis of the structures. And then we produce not to satisfy the condition of ultimate limit state, but we produce something like we satisfy conditions of global safety factor of the checking of the structure.
But is the design driven by service limit state or ultimate limit state?
Normally by service limit state, because normally it is the pre-stressed structures, and we have to satisfy the condition of the stresses.
Okay, so another question about the segmental bridge. I think that was probably answered in your presentation. The question was about the resin or grout used for the joints. Or is there any special couplers used for the ducts between the segments, whether tendons grouted or ungrouted, and what was driving the selection, whether to grout or not?
I think I have this in my presentation. Special couplers are used. and also the tubes after the finishing of installation process are filled by the concrete, normal concrete. So it is completely filled by the concrete members, and through the joints, these special couplers are used, and I think everything will be okay.
And what exposure class was assumed for this bridge?
It was a standard. It is a X. If I describe it, XF4.
XF4 chloride.
Yeah.
Okay. There is another question about the surface of. You spoke about it, but one of our colleagues touched surface and it was very painful because of the exposed fibers. Is there any new developments in treating the final surface, or is the fibers are still exposed, or is it rough? Is it not rough?
It could be a problem. It could be a problem. But when you put your hands on the surface, you can feel the fibers sometimes. Yeah. Sometimes it is possible to use a combination between the steel fibers and polymer fibers. And the polymer fibers could join the steel fibers in the surface area and move it a little bit deeper. So then you will obtain, for example, 5 millimeters without fibers, and fibers are situated a little bit lower. But for the touching, there is no problem with the, it is not painful for you, and the fibers are situated a little bit lower, and then it is possible. Now we are still thinking about it and still to develop how to produce the upper surface without the fibers and move it down. It is still under point of research.
But I suppose you don't slip then on the bridge.
Yeah.
Okay, there's another question about is there a reduction in bursting and spalling in the anchorage area when you use UHPC? Would that be also interesting in the terms of advantage of using or reducing concrete volume?
Yeah. Of course. We could reduce a lot of the volume of the reinforcement, and also, for example, length of the transmission length between the rebars and between the steel. It is very possible to use it, and also the thickness of the member. When you put their anchorage of the prestressing pendants, you could reduce the thickness. So it is a very beneficial.
Another savings there. Another question here: what size of the mold was used for the flowability test?
What size of
mold?
It was it is difficult. I don't remember it now.
Okay. Maybe you can get the email the question and you can think about it.
Yeah, I'm sorry.
Okay, thank you. I think we also spoke about this. What was the feedback from the precast supplier? How difficult was it for them to produce UHPC elements? And you said it's a know-how, so I think they are keen, but not sharing how they produce it.
Yeah, they don't want to share the right definition of the mixture. I think that now the materials properties and how to obtain it by the mixture, it is well known. Very often it is the problem of the definition of the shape and the geometry of the element. So if you, for example, also compare the price for the definition of for the producing of this element, the one part of the price, one part of the price is the price for the material, and the second part, and it is a little bit equal to the first part, it is the price for the formwork. Because very often it is the steel formwork we have to use. It is a reusable formwork, and the price is very high. So now I think it is not a problem of, as I said, of the mixture. It is the definition of the geometry and producing of the formwork.
Okay, so I guess that goes hand to hand with the second question that's been often asked here about the economical comparison between UHPC and normal concrete. I think that's a big question that people are worried about. That
if you compare it, I think now if you compare only the price for the construction and for the structure, it is the equal. So it is the structure from the UHPC to the normal concrete. But if you take into account also the price for the maintenance, for the price, for example, something like consumption of the materials, consumption of the CO2, the UHPC is much more, is very better. It is a better solution to use a UHPC.
So if you think about the total life cycle cost, you think UHPC is a better solution.
Yeah.
So the material is probably more expensive, but the volume is less, and then the cost associated. Okay. And a question here that we spoke about some testing of the material, the Flexure Strength. The tests were on was it a 4-point bending test?
It is a 4-point bending test. Yeah, typical.
Okay. That is done. Sorry. Could you please explain again the construction of the segments, how the way they're put together? And I think we spoke about it. That's when you had the precast segments and you put the glue on them and then you pressurize them by using the post-tension cables, right? That's how you do it. Okay. Question here, as I said, there was also a couple of times, and you spoke about just now, it's about the embodied carbon of UHPC compared to traditional concrete with similar material sources. So can UHPC be beneficial in reducing the total carbon footprint of such structure?
Yeah, of course it could be a benefit. Yeah.
Is there studies? Was it measured now? Is there a specific comparison of how much we can reduce?
There is lots of studies, but these studies, it depends on the definition of parameters for which type of structure the studies are described. For example, if you compare the studies for the structures for buildings, for example, the UHPC is a winner. It is very good. But for example, for the bridges, and very often it is the question of the life load, and especially the effect of the transport of the precast elements. In this case, it is not so good comparing to the building for the bridges, but still the UHPC is better comparing to normal concrete. Okay,
that's interesting. Another question here about the voids. I mean, when you filled up the box bridge, you would say, with the polystyrene, would you remove it after it, or do you keep it in there, or if you remove it, how do you remove it?
It is not removed. The polystyrene is still in the bridge, and I hope it will be till the end of the service life.
So there's no inspection from the inside then?
No, because normally it is impossible to design this type of hollows without any possibilities of inspection. So we want to reduce the volume of the concrete, and we don't want to produce some hollows to put there, for example, small camera. So the way is to fill the box with the polystyrene.
Okay.
It is, for example, it is used in Austria for normal reinforced concrete, because very often they used normal reinforced concrete without prestressing, and they produce a reduction of the cross-section area by the hollows, and these hollows are filled by the polystyrene. It is normal and cheap solution.
But you really make sure that the polyst doesn't float. Huh?
Yeah, of course. In this case, it is necessary
floats up,
position. Yeah.
So there's another question when it comes to the life cycle cost. Would you have a number in mind in percentage between a UHP FRC bridge and a conventional precast girder? I mean, it's difficult to compare, but
maybe UHPC, the benefit is 10-20%, something like this. It will be.
Yeah, I suppose it's difficult to say. Depends on the span of the structure, number of girders. Yeah, so it's difficult.
But I think that if we go a little bit to the future, I think it will be better for the UHPC, because now it is something still a little bit new, and also we try to understand the behavior of the material. If we will have much more results from the research, I think it will be again better.
Okay. So with that being said, we also don't have now codes of practice or standards. We're still experimenting, so it's a design by experiment.
Yeah, by recommendations and by the testing. Very often, for example, if we produce the design of the bridge, for example, if we produce the design of these two bridges, we have for example, 5 segments which will be used for the superstructures, and 1 segment we have for the testing. The one part of the testing is the testing of the geometry and also the testing of the formwork. And also for us, it is very good because we could destroy it. So we could define the final for the ultimate limit state of the segment.
So I suppose it's quite a benefit now to monitor the structures that you design than to obtain data. So do you guys monitor as well?
Yeah, we use a lot of monitoring, especially for example, development of the strain, the development of the prestressing during the service life for this type of the structures, and because it is a new type of the structures, and we could obtain the financial support from the client and from the, for example, from the government, because they want to supply us for the studying of the new material.
Yeah, so this could be very useful then in development of the standards then, if you have this information. How do you optimize the granulometry of the UHPC in order to maximize the density?
I have to say I don't know, because as I said, it is the question for the contractor of the UHPC mix, and it is a secret. But it is done. It is done. I'm only user of the UHPC.
So here's the question. So we mentioned that the carbon is lower, but you're doubling the cement. So how does that work?
Yeah, but I doubling the cement, but I decrease the volume of the concrete.
So in the end, you have less cement.
Yeah, finally, I have less cement compared to the structure from the normal concrete.
Okay, that makes sense. Do you have any isolation against water and chlorides? But I think you mentioned that that's nearly impenetrable.
No isolation or waterproofing, no.
Because the material is so dense that there's no ingress. There's a question here, I mean, probably it's hand-to-hand with that, about the durability. Would the freeze thaw and would be an issue, freezing and thawing and stuff? Is that an issue for your HPC, or is that fine?
It is not a problem. It's not a problem.
Okay.
Lots of tests were made for this behavior, but still no problems for the freezing and freezing cycles. No problem.
Okay. Another question here. I mean, we spoke lots about precast, but what do you think about using UHPC as an in situ? Would that be possible or difficult? Maybe
sometimes in the future it will be possible. It is a question of producing the mixture, because normally you have a very short time between the mixing of the concrete and between the casting, because the strength of the concrete increased rapidly in the beginning of the hydration process. So because the volume of the cement in this mix is very high, as I said, so the speed of the hydration is very high. And also it is the question about the drying shrinkage, because now the drying shrinkage is very important and is a little bit higher comparing to normal concrete. So if we will solve this problem, for example, we will use something, it will be possible to use some additives to a little bit decrease the speed of the hydration process and also decrease the total drying shrinkage, then it will be possible to use UHPC casting in situ. Now it is possible, but for the small volume, for example, maximum volume, casting in situ could be 0.5 till 1 cubic meter. It could be possible. Okay. But also it is the question about the dimensions of the members. It is better, for example, to produce long, thick members comparing, for example, to big cylinder, big cube.
Okay, and I suppose with the tolerances as well. I mean, if you have 5 mm tolerance in situ, that's much more difficult to.
Also, it is a question of the hydration heat, because the hydration heat is very, very high.
Yeah, there's a question, and I think we spoke about it. Yeah, the connections are achieved by the glue, as you call it, and prestressing. So we can tick as answer it. UHPC perform in terms of carbon dioxide emissions related to strength. I suppose so can you relate somehow the strength of UHPC to the carbon dioxide? Is there more CO with larger strength, but I suppose that you can save on the volume again, so it's a balancing game.
I think it is the same. I think it is the same, because we could reduce the volume of the concrete, because we could reduce the dimension, and we could reduce the dimension due to the behavior, due to the basic mechanical behavior of the concrete, due to the strength of the concrete. So it is connected together.
Okay, and what fibers you mentioned? Is it steel fibers normally, or
it is the steel fibers, and very often it is a combination between the steel fibers and polymer fibers.
And are they deformed, the steel fibers?
I'm sorry?
Are they deformed?
Yeah.
So it's mechanically deformed, or?
Yeah.
Would it be possible to give an order of magnitude price of UHPC? So how much would it cost?
Normally, the cubic meters of UHPC is 1,000 euro approximately.
1,000 euros for a cube.
Yeah, cubic meter.
Okay. Do steel fibers appear on surface? We have discussed that they do, but we're seeking ways how to avoid that. Codes of standards have formulation.
What is also answer for this question, because if some fibers appears on the surface due to the corrosion, in sometimes they will disappear. Yeah, because, but it depends. It is the question of the time. Yeah.
There's a comment here that UHPC in Canada is about $5,000 to $6,000 per cubic meter. So that's interesting that there's an order of magnitude.
It depends what is the price, because if you only compare the price for the material, it is, as I said, the 1,000 euro per cubic meter. If you put to the price of the material also the price for the formwork and also the for the production of the precast elements, it is increasing, of course.
Yeah, so there's a difference between material only and placed product.
Yeah.
So do COSA standards have the formulations for fiber? No, we discussed that. There's really no code so far. Okay. Did you need to define post-cracking tensile strength for the design? And if yes, how did you define it? Or were the UHP FRC elements uncracked in every load combination and limit states? So I suppose the question is, you tell the manufacturer that you want this type of post-cracking tensile strength. Is that correct?
Yeah, it is correct. Yeah.
So the definition.
Yeah, but normally we define for our analysis, especially it is not a global analysis of the bridge, because the global analysis of the superstructure, it is to satisfy, or the reason is to satisfy the conditions, especially of the stresses in the joint area. But for the ultimate limit state, it is, for example, maximum value of the point loading situated on the surface of the UHPC element. In this checking, it is possible to use a non-linear analysis of the material. It is analysis based on the non-linear behavior of the material. We take into account the results of the testing of the material, and also we could take into account the testing of the segment, which is produced. Yeah. Okay. And then it is a non-linear analysis.
Yeah. Okay, we still have some questions here. We're running a little bit out of time. I think we have to be done in, let's say, 15 minutes time, but we still have some, and let's see if we can answer them. Could you tell us what are the critical facts for structural evaluation of UHPC bridges for maintenance purposes?
For maintenance, I think if during construction you produce everything with high quality without any problems, if you satisfy the conditions described by the design, the price for the maintenance is relatively close to the zero, because you don't have to do nothing with the structures due to the service life. For example, you have to change the bearings, of course. Yeah. You have to change the expansion joints. But for the superstructures, because you don't have a waterproofing, you don't have special layers for the movement, I think it is the zero. But what is important to say, we have only, for example, 10 or 15 years experience with the UHPC, because it is a very young material. We don't have still only this experience. But if you compare behavior in 10 years of UHPC with normal concrete, with UHPC you don't have no problems. It is a resistant for the chloride, for the acid, for everything. So I think it will be also in the rest of the service life, in the rest 19 years, it will be the same. So no problems, no maintenance, no price.
Okay. So I suppose if you make it fully integral, then you don't have to worry about the bearings and expansion joints.
Then it is still the question also about the, for example, solution of the terrace, solution of the prestressing, because in this stage, the problem could be with the prestressing. With, for example, solution of the details, with waterproofing of the prestressing, or with details of connections between the prestressing and the superstructures, with anchorage of the prestressing, it could be a problem. But with UHPC, it is for every time.
Because there was 2 failed bridges, I mean, recently because of the corrosion of the cables, right? Yeah, the Morandi bridge and then the bridge in Prague.
In Prague, yeah.
The cable stayed bridge, how did you achieve the transfer stability during the construction? For wind example, if there was a high wind, was there any special measures in place?
The stability of the structure is done because the shape of the pylon is A shape, and also the shape of the hangers in the A. So it is going through also in a horizontal direction. There is some inclination of the cables. So the stability is done only by this geometry solution. No other additional tendons or hangers were used.
Okay. And what would you say is the minimum thickness for UHPC panel for structural use?
Normally it is defined by the length of the fibers. And because we think about the fibers length approximately, for example, 5 millimeters maximum, The minimum thickness which is now possible to produce is 25 millimeters.
25 millimeters.
25 millimeters. We have a very nice pedestrian bridge here in Czech Republic. It was done during the research project. It is the U-shape single span beam. It is very nice. It is with curvature, and the thickness of the wall, it is only U-shape without any transverse beam, without any special increasing of the stiffness in the abutment area. And the thickness of the wall is 35 millimeters without any prestressing, without any bars, only UHPC. And the length of the span is, I think, 6 or 7 meters. Okay,
that's quite interesting. We spoke about fire resistance. We said it's quite good, but is there any values on fire resistance? How about explosive spalling? Would that happen?
I don't know directly. There is some rules from the research, but I don't know directly what is it.
Okay. Can you relate, or how could you relate the strength of the cube to the actual member size of the concrete? Well, I think that's a problem that's prevalent even in normal reinforced concrete, that the cube is not what you get.
Of course, it is very nice, because if you decrease the volume, if you decrease the dimension of the cubes, you will increase the strength. It is very nice for especially for the client. It is a very good way how to say we will have a special structures. But normally we use results from the standard dimensions. That means from the cubes we use 150 millimeters, and we use this value of the strength. If we go with the designing to the edge, as I said, for example, if we use a special element, then we test it in a scale 1 to 1. So if we want, for example, as I said in the beginning, we want to test the UHPC element for the point loading, we prepared 1 to 1 scale element, and we will test it. And this is for us the conditions for the designing. But normally we have to satisfy the results from the elements described by the standards for the testing of the concrete. Okay.
Another question here, I think we already spoke about it, about cracked UHPC and if you should nonlinear analyses or not. I mean, I think that was discussed. What is the criteria to calculate the depth of beams related to clear span? I suppose we have for normal concrete 1 to 20, 1 to 25. So for UHPC.
It is one for the single span bridge, it is 1 to 44. Then it is important to say it is not a question of the stresses, because you could satisfy the question, satisfy the conditions of the stresses. Then it is problem of the deformations, and sometimes it could be a problems of the vibrations. So then the design is dependent on these two levels. But it could be solved, for example, because the modulus of elasticity is a little bit higher comparing to normal concrete. So also if you decrease the depth of the cross section, the stiffness is not so limited comparing to normal concrete.
Question here in the forum. I think you spoke about it, but how do you prevent the polystyrene from floating? So you had some mechanical device.
Yeah. It was a special bars. We have special steel bridge situated above the casting area of the UHPC element. Above the bridge, special concrete box was there put it, and by the bars, it was connected between the polystyrene, between special steel plates situated under the polystyrene, between the polystyrene and between the concrete bars. So the position of the polystyrene was fixed in the right position, in the right depth of the concrete during the casting.
And is it a one cast or two cast or three cast? Is it
one cast? Only one cast.
One cast. Okay. Yeah. Just all at once. Okay.
Yeah.
We have discussed footbridges here in your presentation, but do you think that UHPC could also be used for road bridges in near future?
I think it will be used. We also produce some design of bridge for the roads. Again, you have to think about it, because now we are in a situation that we could produce only precast elements. So we could produce, for example, segmental bridge from UHPC. It will be possible. Or we could produce only some parts of cross-section of the superstructures. Very often it is possible it will be possible to use it, for example, for the box girder. And instead of casting in situ walls or slabs, it could be possible to use precast UHPC elements. For example, for the balanced cantilever method, instead of the casting in situ walls, you could use precast elements, and then you will produce, it is called butterfly webs solution of the box girder, and for the walls are used UHPC elements. It will be very good and it will be very useful because, again, you will reduce the self-weight of the structures. You will reduce the self-weight of the structures, especially during the construction stages. Then you can reduce the prestressing and you could reduce the price for the bridge.
Okay, we have a couple minutes left, so maybe I'll just ask some questions. I'm going to just pick some. I'm sorry if we don't answer all of them, but what do you think about 3D printing of UHPC? Do you think that's going to happen in future?
Maybe it will be the future. Yeah, why not?
I suppose the fibers will be a bit tricky to get.
I think it will be
through
without
the nozzle.
fibers. It will be without fibers, but normally, normal pure UHPC, it will be possible.
To print. Is there any restriction on aggregates to be used for UHPC? There's a comment here at Okinawa that contractors just use sea sand and wash it to get rid of some of the chloride residues.
Yeah, it is very special restriction, but again, I have to say it is the question for the contractors and for the definition of the mixture of the UHPC, and it is the secret, but special restrictions are important. Okay.
And can you repair damaged UHP FRC?
It depends what kind of damage we are speaking about. Small cracks, it is not a problem because we could, on one side, it is possible to use self-curing of the UHPC. Also, it is possible to fill the cracks, fill the hollows by the material, for example, based on the UHPC behavior. It is not a problem. But for example, if you move some part, for example, some part of the upper area of the cross section, I think special material based on some polymers and something like this could be used. What will be important to produce the right connections between the UHPC and between the new materials, because for the normal concrete it is possible, it is not a problem, but we work with lower strength in normal concrete. If I want to replace, for example, one layer of the UHPC with another material, the connections, especially the shear connections in the longitudinal section, longitudinal direction, it will be difficult.
Yeah.
Only by the chemical contact.
Chemical bonds, so yeah. Delamination could be an issue. Okay, so last two questions, maybe just quickly. Do you have any special considerations when designing precast segment formwork and the high early shrinkage, I think has been discussed? And what would you recommend as a method for controlling the effect of thermal expansion to prevent cracks happening in UHPC? I suppose
very often, especially when the volume of the UHPC concrete is high, we put special sensors in the casting element, and we try to measure the temperature development during the casting. And for example, again, we have the one segment for the testing. So if some cracks will appear, we, for example, change the dimensions, change the geometry, or it is possible, for example, to casting divide to two parts or produce some hollows, something like this. It is possible.
Okay. Well, time is up. Sorry if there's maybe perhaps some questions from our colleagues, but your emails have been provided, and I think you're happy to answer per email as well.
Of course.
So I'd like to thank you, though, for presenting and doing this for us, for the national group here in South Africa. And as we said, that it's the mission of IABSE to share and knowledge and to further educate all of us. So thank you very much for the interesting presentation, and thank you for all of you attending and for asking very interesting questions. So thank you very much, and bye-bye.
Thank you very much also, and enjoy the rest of the day and enjoy the weekend. And thank you very much once again. It was a very nice time for me and great pleasure for me. Thank you.
Thank you. Bye-bye.
Bye-bye.